Hey guys, I am going to show you how to solve one of the electrostatic force problems that has forces that are in a three-dimensional arrangement. Or yeah, three-dimensional arrangement, two-dimensional arrangement, not three. That'd be even more difficult. So a problem with multiple charges in a two-dimensional arrangement. So without further ado, I'm going to share my screen. I'm going to pull up, I'm actually going to walk through problem number 6 of the practice problems. It's one of the ones you have to solve, but this will hopefully help you understand how you go about doing the solving of that. So I'm just going to share my screen and pull it up and we'll get started. Okay, here we go. So actually, let me grab the problem and read you the actual problem. I think it basically just says that you have a problem arranged as follows. Let me look at it. It says 3 charges are arranged as follows. And you can see it's basically the picture I have drawn right there at the top of that first page. And it says, what is the instantaneous electrostatic force on the negative 1.2 millicoulomb object? Okay, now, a couple things to talk about before we jump into how we solve this. The first one is to look at the charges on these, all of the charges positive or negative on each one of these charges. So we have a negative 1.2 millicoulomb charge, we've got a positive 1.2 millicoulomb charge, and we've got a positive 2.4 millicoulomb charge. And what they've given us is the 2 separate angles between each one of these, and then we're asked what's the electrostatic charge on this one here, the negative 1.2 millicoulomb charge. So just like you've done before, in situations where you have things that are in 2 dimensions, you have to analyze, or more than 2 objects, we've got to analyze basically the charge, which we'll call F1, between the negative 1.2 and positive 1.2 millicoulomb charge. And then we will also create a force between the negative 1.2 millicoulomb and the positive 2.4 millicoulomb charge. So then we'll have these 2 forces. What do we do then? We do what we've done in the past. We break them down into vectors. We add the x components, we add the y components, we find out the magnitude and the angle using trig functions. Okay, so that's what we're going to do. Let's go ahead and walk through it. So the force 1, is F1 that I'm saying here is between this, again, the negative 1.2 millicoulomb and the positive 1.2 millicoulomb. And you guys know the equation for that. It's F equals K Q1 Q2 over R squared, right? K is 9.0 times 10 to the 9th newtons meters squared per coulomb squared. Our charge, negative 1.2, it's kind of hard to see here, times 10 to the negative 3, right? Because this is a millicoulomb, right? Times the positive 1.2 millicoulombs, 10 to the negative 3rd coulombs, divided by my radius, which they have given as 0.4 meters squared. Now, you'll notice I did not put any pluses or minuses. There's no charge. There's no indication of the charge in this equation, right? We're just going to come up with the force. When we do that, we're going to get the force of 8.1 times 10 to the 4th newtons. Now, how do we know the direction of that force? Well, we're looking at this positive 1.2 and a negative 1.2 here, right? So they're opposites. We're talking about how this particular, sorry, my annotation stuff's popping up, hang on here. How this charge is affected. Of course, this charge, if it's negative, and this one over here is positive, it would move, the force is going to act in this direction toward the positive charge. So that's how we draw this force 1, okay? Let's go ahead and look at the equation for force 2. Same exact equation. I'll go ahead and scroll down here. Negative 1.2, there's the 2.4 positive millicoulomb charge here. We have a radius of 0.2 meters. We end up with a force 2 of 6.5 times 10 to the 5th newtons. Again, I'm going to scroll back up here a little bit. Again, this is a negative charge. This is a positive charge. We're asking about how this charge is affected. Of course, it would be drawn toward the positive charge. So the force is in this direction. Okay? Now, why is that important? Because that gives us the angles for these particular, what we're going to use to break out into the individual vectors in the next part of the problem. Now, one thing I want to say just real quick, I'm going to pull my annotation tool up here. Suppose that this was a positive 1.2 millicoulomb charge, okay? Then how would that impact the overall problem? Well, what that would do is instead of my force moving in this direction towards the positive, right? If this was a positive and this was a positive, this positive charge would be pushed away. So the direction of my force would actually be like that, 180 degrees from what I'm showing here. Because obviously if this was positive and this was positive, then this charge would be repelled from this charge, meaning the direction of the force would be out here. I'm just showing you that because there will be other problems that will not be opposite charges, and you'll have to know how to handle that. So, okay, I'm going to undo that. Okay, and we can move on. Stop. Hang on, I'm going to get rid of my annotation. Oops, get rid of it. Okay, now I'm going to scroll down here. So we've got the two charges. We've got the placement of them. You can see I've written it again. This is actually the first part of the same problem, but I had rewritten it to make it a little easier to see. So, but we still have, here's our charge, F1. Actually, let's go all the way down here. I have it drawn out specifically. Okay, oops, let's not do that. Okay, so here's my charge. Here's the 8.1 times 10 to the 4th Newton charge, force, excuse me. Here's the 6.5 times 10 to the 5th Newton charge. Okay, so now we've got it just like you've done in the past. You got to break that baby up. So we're going to call this one A, the 8.1, and we're going to call this one B. Now, another important thing to recognize is we can't just use 19 and 75 as our angles. Why? Because we always measure angles from the positive x-axis. So what is this angle here? Well, it's actually 360 minus 19, right? Because if it went all the way around, it'd be 360, but it's 360 minus 19. So we actually have an angle of this first force of 341 degrees. Well, what about the second force? Well, this is 75 degrees, but from the y-axis, I mean the x-axis over here, right? So we would take the 180 here to here, oops, here over to here, right, would be 180 plus 75. So we're going to have an overall angle of 255. So then it's just what you already know how to do. Take the force, 8.1 times 10 to the 4th newtons. For the x dimension, of course, we multiply by the cosine of 341. For the y dimension, we multiply by the sine of 341, and we get these numbers. We get a force that is 7.7 times 10 to the 4th newtons in the positive x direction. We get a force that is negative 2.6 times 10 to the negative 4th in the negative y dimension. If we scroll down here and look at B, oh, I'll leave that up there, I guess. B, same thing. When we do the 6.5 times 10 to the 5th times the cosine of 255, we get negative 1.7, which again is right there. We get negative 6.3, which again is right here. And then we're going to go up to the next point where we're going to add those vectors. So the A of x, 7.7 positive, the B of x, negative 1.7 times 10 to the 5th negative, right? We get negative 9 times 10 to the 4th newtons. When we take the C of y, we take our A sub y, negative 2.6 times 10 to the 4th, B sub y, negative 6.3 times 10 to the 5th. Add those up, we get negative 6.6 times 10 to the 5th. Those are the vectors of our magnitude. It's not the magnitude, it's just the x and y components of it. So of course we need to use really the distance formula to figure out, Pythagorean theorem, however you want to call it, right, to figure out what the length or of the magnitude would actually be. And we get an actual magnitude of 6.7 times 10 to the 5th newtons. Now, to figure out our angle, what do we have to look at? Well, we have to look at these vectors. Of course, it's negative, the inverse tangent of C of x, C of y over C of x, so right? So we have negative 9 times 10 to the 4th newtons in the, that's a negative, right, in the x dimension. We have a negative in the y dimension. So what does that give us? It gives us something in the 3rd quadrant, right? If we were going to draw, if we're going to draw the resultant vector, it'd be something like that, right? That's not very good, but you get the idea, right? So that means that we are going to take whatever angle we get, and get rid of that here. Oops. We're going to scroll down here. So we're going to add, we get an angle of 80. We're going to add 180 to it. So that means that our angle would be 260 degrees. I also want to show you real quick, these numbers down here show how I did the adding of these, right? Negative 1.7 times 10 to the 5th is negative 170,000. 7.7 times 10 to the 4th is 77,000. Of course, I actually get negative 93,000, but I only have precisions to 10,000s. So I've got to round that and let it be negative 9 times 10 to the 4th. Same thing on C sub y. I get negative 630,000. That's this number here. Oops, sorry, this one here. Sorry, negative 630,000. I have negative 26,000. When I add those, I get negative 656,000. However, again, precision to 10,000s. So my answer is negative 660,000 or negative 6.6 times 10 to the fifth newtons. So gotta remember how to do that adding and subtracting using significant figures. And then our final, again, angle is 260. So our final answer is that we would have an electrostatic force of 6.7 times 10 to the fifth newtons, and it would be at an angle of 260 degrees. There you go. I hope that is helpful. I'm going to go ahead and stop sharing that document, and I will look forward to seeing you at for the next video that I make. All right, thanks. Bye.